Hello everyone, our research project is the design and simulation of mixed signal electronic circuits. Our group members are myself, Katie Huang, Jennifer Gray, Anthony Sellers, Ernest James, and Abram Jones. Our project goals. Our goal is to simulate high speed and low power mixed signal circuits in Multisim and to learn about circuits in their applications. As a result of not being able to access a lab environment, instead we chose to simulate circuits in Multisim. Multisim is a software that allows us to design circuits and simulate their performance as they would be in real life. And second, to learn about circuits and applications. This is because mixed signal circuits are becoming more and more widespread in smart devices, especially as SoCs or systems on a chip that power small devices wired to different analog sensors. In this sense, any device with a sensor that also requires computing power will have a mixed signal circuit. And then a brief introduction to parts of our study. As mentioned, Multisim is a software that we used to conduct our simulations. And Multisim is also a tool used by engineers, which is important because by using this software-based circuit simulator, engineers can test a circuit before it is fabricated to make sure it will function properly and efficiently. Next, we learned about basic components of circuits, such as transistors, wires, and different types of meters. And these are important because we will use them to build more complex circuit systems later on. We also learned about different metrics of circuit performance. Most importantly, voltage gain, which is the measure of the input voltage as related to the output voltage. It is also mentioned as amplitude or magnitude. And we also talked about circuit current, especially current in relation from the input to the output. And finally, the importance of mixed signal circuits. As mentioned before, many electronic applications use mixed signal circuits as systems on a chip because these small devices contain analog signals from analog interfaces such as sound, video, and temperature sensors. However, because they also require signal processing capability of digital circuits, they need analog to digital converters to convert analog signals into understandable digital format. In addition, mixed signals systems on a chip not only reduce the size, but also help in reducing power consumption. And because of this, the reliability of the overall circuit system is increased, and these are primary reasons behind the adoption of mixed signal systems on a chip.
Hello, I am Jennifer Gray. Methodology, learning multisim, laying out circuits in multisim, simulating circuits in multisim. Multisim provides for circuits to be built with drag or drop of components and connected via wires. Circuits are simulated directly in multisim as if they were turned on, and virtual meters are used to collect data. We will have to find the components, then link them together by the wires. DC sweep increments the voltage or current of a selected source and predefines steps over a range of values. AC sweep is useful for analyzing the frequency response of a circuit. Parameter sweeps analysis allows you to run a series of underlying analysis on different parameters or variables of the circuit, like temperature, resistance, and etc. Our biggest challenge was understanding a new software. Everyone in the group was not familiar with Multisim, or they were new to learning Multisim, so that was a big challenge in learning everything about Multisim.
And here we have a demonstration of one of the circuits that we simulated in Multisim. So this is an analog digital converter. It is an 8-bit converter, so on the right you can see two black displays and then sets of LEDs. And if I start the simulation here, the LEDs will start to light up as the voltage input changes, and also the black displays will count up in hexadecimal, responding to the different binary inputs. The LEDs are flashing when it's 1, and so this counts up in binary as well as hexadecimal. On the left, you can see the meter at the top, which changes according to the voltage changes in the analog component. However, the meter is a little bit delayed, so it's not accurately representing the voltage that is being shown, but more showing that the voltage is changing. And then here I changed the data used to increment the voltage just to show the circuit counting up a little bit more quickly, just to show the wide range of values that this 8-bit circuit can convert.
Results. Left to right, you'll see junction field effect transistor, known as JFET, bipolar junction transistor, known as BJT, and lastly, you'll see metal oxide semiconductor field effect transistor, known as MOSFET. These are basic components that we will use in later circuits. The BJT-based amplifiers and the CMOS and MOSFET-based amplifier. Here's the layout of the IV curves of a junction gate field effect transistor known as JFET. It shows the relationship between the drain source voltage and the drain source current. The max drain source current changes based on the gate source. Because the junction field effect transistor is a control device, no current flows into the gate. The junction field effect transistor has a narrow piece of high resistivity semiconductor material forming a channel of either N-type or P-type silicon for the majority carriers to flow through with two electrical connections as either and commonly called the drain and the source respectively. Here's the layout for the IV curves of a bipolar junction transistor known as BJT. The characteristic curves predict the performance of a BJT. There are 3 curves. 1, an input characteristic curve. 2, a transfer curve. And 3, an output characteristic curve. The most useful curve for amplifier design is the output characteristic curve, and that is what's being displayed in the layout above. Here's the layout of the IV curve of a metal oxide semiconductor field effect transistor known as MOSFET.
Results. Design and simulate BJT-based differential amplifier using a multi-system software. Analyze the DC and AC response property of the circuits and the effects of different parameters of the voltage gain of the amplifier. Results. Temperature dependence of voltage gain. The purple line has at its lowest has a magnitude of 1.0 with the application of a temperature of 200 degrees. This graph shows the magnitude and the frequency throughout the graph. The phase in the frequency is shown also throughout the graph. The purple line decreases at about 100 megahertz. Effects of load resistance on the voltage gain, device parameter sweep. The magnitude and the frequency. The green line shows the magnitude of 100 with being at its lowest of about 1,000 at about 100 magnitude, and its maximum value is about 1K. The green line also at its lowest in the graph with the magnitude of about 10 meters. The application shows the capacitance at its lowest with the magnitude reaching 1K. Results. Design and simulate CMOS-based operation amplifier using a multi-system software. Analyze the DC and AC response property of the circuit and the effects of the temperature and load resistance and capacity of the voltage gain of the amplifier. Frequency and response of rail-to-rail op-amp. The frequency response of rail shows the magnitude and the frequency with the magnitude being approximately 100 and the frequency decreasing at 10 gigahertz. In this graph, this is the temperature dependence of voltage gain, temperature sweep. In this graph, the purple line shows the magnitude between 1 through 10 with the application temperature being 100 degrees, with the line decreasing at 10 gigahertz. Effects of load on the voltage gain, device parameter sweep. This graph shows the magnitude between 1 and 10 with its maximum volume of 10 magnitude and decreasing at 10 gigahertz frequency. Effects of load capacity on the voltage gain device parameter. With the green line starting off at the lowest is about 10 magnitude with increasing to about 100 magnitude. And it stays the same throughout the graph, increasing at about 10 gigahertz frequency. Effects on power voltage on voltage gain. Also in this graph, the magnitude is about 10 with the application of about 5 degrees and decreasing at about 100 megahertz frequency.
For the results, we designed and simulated CMOS base 2-stage amplifier using the Multisim software. We analyze the DC and AC response property of the circuits and the effects of temperatures and low resistance and capacitance of the voltage gain of the amplifier. The image on the bottom is a simulated two-stage amplifier. It has 11 transistors and 1 capacitor. On the left is a CMOS-based two-stage operational amplifier DC transfer characteristics. As you see on the graph, on the x-axis is the voltage and on the y-axis is the current. The current will start at 0, and as the voltage increase, the current will increase automatically. Then when the voltage keep increasing, the current will level out throughout the whole graph when the voltage increase. Then on the right is the CMOS-based two-stage operational amplifier AC suite. On the top graph, the x-axis is the frequency and the y-axis is the multitude. Multitude starts at 10, then when the frequency increases, the multitude increases as well. Then when the frequency keep increasing, the multitude will level out until the frequency hit 1 megahertz, then it decreased to 10 magnitude. Then at the bottom, the frequency is on the x-axis. On the y-axis is the phase degree. The phase degree will be at negative 100 degrees. And when the frequency increase, the degrees will decrease. And when the frequency keep increasing, then the phase degree will level out. It will do that throughout the whole graph until the degree is at negative 400. In these graphs, CMOS-based two-stage operational amplifier temperature suite. The x-axis would be on the frequency, and the y-axis the magnitude. The magnitude will start at 10. And when the frequency increases, the magnitude will increase. Then when the frequency keep increasing, the magnitude will stay level throughout the graph until the frequency hit 1 megahertz. Then magnitude will decrease automatically until the magnitude hits 10 magnitude. And at the bottom, the y-axis is phase degree. The temperature would be at negative 100, but when the frequency increase, the temperature would decrease. Then it will level out. And when the frequency keep increasing, it will drop again. Then it will level out once again when the frequency keep increasing until the phase degree is at negative 400. In these graphs are the effect of load resistance on the voltage gain device parameter suite. The x-axis is still frequency, and on the y-axis is megahertz, magnitude. The magnitude will start at 10, then it will increase when the frequency increase. Then the magnitude will level out when the frequency will keep increasing until it hits 1 megahertz, then it will decrease automatically until the magnitude is at 10 magnitude. And at the bottom On the y-axis is the phase degree, and the x-axis is still frequency. But the phase degree will start at negative 100, somewhere around negative 100. But when the frequency increases, the degrees decrease. Then it will level out. When the frequency increases, then it will do that, the same thing throughout the whole graph until it reaches negative 400 degrees. And these graphs are called effects of low capacity of the voltage gain device per meter sweep. On the x-axis is the frequency and the y is the magnitude. The magnitude will start around 10. Then when the frequency increases, it will increase a little, then it will level out. When the magnitude level out, a certain frequency will hit 1 megahertz, then it will decrease automatically until the magnitude is 10 M. And at the bottom, the y is the phase degree. And the phase degree will be somewhere around negative 100 degrees. But when the frequency increase, the degree will decrease. The phase degree will decrease. When the frequency keeps increasing, it will level out. The phase degree will level out, and it will do the same thing throughout the graph until the degree is negative 400 degrees.
We simulated an operational amplifier from the Multisim library using the Multisim software and compared it with our designs. We analyzed the DC and AC response property of the circuits and the effects of temperatures and the load resistance and capacitance on the voltage gain of the amplifier. To the left is the layout, and to the right is the symbol. Here's the AC sweep for standard operational amplifier. So we use this one for comparison. This shows the AC sweep, of course. For the top, X is frequency and the Y is magnitude. When the frequency increases, the magnitude increases. For the bottom, X is frequency and Y is the phase. When the phase decreases, the frequency decreases as well. Here's the temperature sweep for standard operational amplifier. The temperature effects on voltage gain. For the top, X is frequency and Y is magnitude. Frequency is negative 100. The lowest voltage gain is 200 at the bottom. So when the temperature decreases, the magnitude decreases. For the second graph is the phase. Phase is X and the frequency is X and the phase is Y. When the frequency increases, the phase decreases. Here's the device parameter sweep for standard operational amplifier. X is the frequency and Y is the magnitude. We simulated for resistance, and the voltage gain will change. When load resistance is different, the phase will change. Here's the device parameter suite for a standard operational amplifier. We simulated 3 capacitance. Y is magnitude and X is frequency for the top graph. And for the second graph, Y is the phase and X is the frequency.
Hey, I'm Ernest James III, and here are some of our results. We simulated an ADC in Multisim. ADC is an analog to digital converter tool in Multisim. The ADC system responds to different power voltages to trigger LEDs. Here, if you look in the diagram at the bottom, you'll see 4 LEDs, and they're all triggered when voltage is applied. We also simulated another type of analog to digital converter. This converter has 8 bits of digital output, and this was demonstrated. Our future work, if and when we're allowed back into the lab, we plan to use some of the simulations that we simulated this summer, and we will fabricate physical circuit boards and test them out. We'll also continue building more circuit boards in the near future. Here are some of our references.